Okay, why don't we begin? So we're very happy today with this special day, normal time, but special day, to have a seminar from our own Steve Shu, who is going to try to spend the next 60 minutes convincing us that black holes actually do have hair.
All right, thank you very much. And Andreas is actually controlling the slide, so I will say advance or go back as necessary. I want to encourage people to ask questions, so I'm going to try to give a very pedagogical introduction to this topic because it's a somewhat specialized topic, but it's also a very fundamental topic. And most of the arguments that will be made will be based on physics, not highly mathematical constructs. So it should be understandable to everybody, but I really welcome questions, and I can't see everybody. So if anybody has a question, the organizer should just stop me and tell me that there's a question, because I'm really happy to answer questions during the talk. So next slide. So here are some references. The first two are physical review letters and a physics letters paper that were just published in the last month or two. The link below, these PDF slides are available from me or from the organizer if you want them. And in that PDF, that everything here is a link. So colloquium, black holes, entropy, and information. That refers to a colloquium that I gave over multiple years, which I think gives an even more pedagogical introduction to this problem, although it mainly just sets up the problem because we didn't really know how to solve the problem back then. I want to recommend two review articles. One is by Samir Mathur, that's the bottom one. And he has given some years ago, I think, what is the conceptually cleanest formulation of the black hole information paradox, which is sometimes called Mathur's theorem. And as a kind of test of the solution that we're proposing, I will run through his theorem and show you where the loophole is that allows our solution to work. So I recommend his lectures on the subject. And then the other review article that I would recommend is by Suvrat Raju. That has just been published in Physics Reports. And he and his group have been working in the last few years on something called information holography, which has to do with whether, to the extent to which the information that's in the bulk of a space-time can be recovered through measurements at the boundary of space-time. And the work that they've done is very complementary to ours, because what they the thing which encodes the information which they show is available through very careful measurements at the asymptotic boundary of spacetime is the quantum hair that I'm going to talk about in the rest of the talk. So next slide. So this problem has been out there since 1976, and there's a very complicated history of it, which I guess I don't have time to go through, but if somebody asks me at the end of the talk, maybe I'll go through it. But roughly speaking, there were already indications in Newtonian gravity that something like black holes could exist. With the advent of general relativity, we could actually find classical solutions in field theory that describe black holes. Once you have those black hole spacetimes, you can compute scattering amplitudes, for example, of quantum fields in that curved spacetime background. And essentially, that's what Hawking did to discover what we now call Hawking radiation. And once you discover that this Hawking radiation exists, it implies that black holes don't live forever, but they gradually evaporate. And then that sets up the paradox, which I'll go into in some detail. Now, to resolve the paradox, we have to go one step further, which is that we have to actually look at the quantum state of the graviton field, which is external to a black hole. And what's interesting about the solution that we're going to propose and the general framework that we're working in is that although gravity is treated quantum mechanically, we are only using a kind of long wavelength or low energy effective theory for gravity. We do not need to know the ultraviolet completion of gravity. So we don't need to know the details of string theory or loop quantum gravity. The whole paradox can be formulated at long distances, and it turns out it can be resolved at long distances as well. Next slide, please. Okay. So everyone is probably familiar with the Schwarzschild solution. That's now over 100 years old, and it describes a simple black hole with no angular momentum and no net charge. The feature of it that I'm going to emphasize is the horizon. The horizon is not really a special place locally. So if you fall into a very big black hole, as you're falling past the horizon, you won't necessarily notice anything special. There'll be some tidal force on you, but If the black hole is very big, that tidal force can be made as small as you like. The important aspect of the horizon is its effect on the causal structure of the overall spacetime, the global spacetime. And I'm going to discuss that in this introduction. Next slide. So you may have heard of something called the No Hair Theorem. It turns out the term black hole was actually formulated by John Wheeler. So John Wheeler coined the term black hole, and then he also coined the term no hair. And the way he used it was black holes have no hair. So what does that mean? If I look at classical solutions in general relativity, which describe black holes, one can show that they are classified in terms of a very limited set of quantum numbers, like the total mass, the total angular momentum, the total charge. And it's only those quantities that are manifested in the external fields that emanate from those black holes. So classically, we would say black holes have no hair. And of course, that limits the amount of information that's available external to the horizon about what's behind the horizon. Now, what we're going to show in this work is that once you take quantum mechanics into effect, you can violate these classical no-hair theorems. And the object that we the thing that we call quantum hair refers to actually the quantum state of the graviton field, which is external to the black hole. Next slide. Okay, so here on the next few slides, I'm going to talk about causality in black hole spacetimes. And everyone is probably familiar with a light cone. So if you look at the figure on the left, inside that cylinder, there's a point, and the future light cone of that point is indicated. Photons travel on the light cone, massive particles travel within the light cone, and it's only spacetime points which are inside that cone which can be influenced by the point. Now, in general relativity, the nature of the light cone at any point in spacetime is determined by the local properties of the metric. And in a black hole spacetime, what happens is that the light cone tips over. So in the figure on the right, if you look at these little light cones, when you're outside the horizon, your future can include future infinity. So you can go forward in this universe, forward in time in this universe, and not hit the singularity. However, once you pass through the horizon and you're on the inside of the black hole, no matter what you do, how hard you fire your rocket engines, or whether you're a photon moving at the speed of light, you cannot avoid eventually hitting that singularity, which is that vertical blue line. And so the causality, the main property of the black hole is the fact that it modifies the causal structure of the space-time. Next slide. Okay. This is what we call a Penrose diagram, and it's a Penrose diagram for an eternal black hole. It's a black hole that does not evaporate. And on this diagram, photons or light-like particles travel at 45 degree angles. So a photon, for example, could start at past null infinity, and it could come in from past null infinity and hit the star before it collapses to a black hole. It could also come in from past null infinity, pass through the event horizon, and then propagate all the way to the singularity, which is that wavy line at the top of the diagram. It's also true that a photon emitted from the star could move at 45 degrees and reach future null infinity, which is on the upper right and the upper left. So this is the simplest Penrose diagram. Now let's go to the next slide. Okay. This is a cartoon, but it actually captures the essential physics of how Hawking radiation works. So we said that the black hole has a horizon, and that once you pass through the horizon, your future is to collide with the singularity. But if you stay outside the horizon, you can reach future null infinity. And what you can think of Hawking having done is look at vacuum fluctuations close to the horizon, but just outside the horizon of the black hole. So we know in the vacuum there are constant fluctuations of, say, particle-antiparticle pairs. You could have, in principle, a fluctuation in which one of the pair happens to fall through the horizon, and therefore it can't reemerge. It has to then fall in and eventually reach a singularity, but its partner can escape to future null infinity. And when you aggregate all of these quantum fluctuations, which are happening all the time, you get a steady flow of radiation from the black hole. And so gradually the black hole loses energy and evaporates. Now, the temperature of this Hawking radiation is inversely proportional to the Schwarzschild radius measured in Planck units. So for an actual astrophysical black hole, this temperature is incredibly low. So, and the lifetime is incredibly long for the black hole to radiate away all its energy. But the key notion here is that, for the information paradox, is that the fluctuations here are happening on the outside of the horizon. So they are causally disconnected from the material that is already inside the black hole. The fluctuations, at least in this picture, cannot know anything about the properties of the detailed properties of the matter that's behind the horizon. All it can know about is, for example, the gravitational potential in the region where the fluctuation is happening. Okay, next slide. Okay, so this is a Penrose diagram, but this one's more complicated. This is the Penrose diagram for a universe that has a black hole which is evaporating and which eventually completely evaporates. And I want to focus on this line, this curvy line, which has the points, the letters A, B, and C on it. And that's a potential world line of an external observer. So you could be an external observer and say you're in a rocket ship or something, and you're going to pass through space-time points A and then B and then C. And I'm just going to describe what you might see at these various points. So at point A, you could look over and receive a photon that was emitted earlier from the surface of the star. So you could see the star. You don't see a black hole. At space-time point B, if you look out from your rocket ship, you might see Hawking radiation, which was is a product of those quantum fluctuations that I described before, which happened again outside the horizon. And then at point C, you could look around and realize the black hole is now no longer there. It's completely evaporated. All of its energy has been converted into the Hawking radiation, which has propagated to future null infinity. And so this is the actual space-time diagram, which is relevant to the information problem. And the information problem really has to do with how does all the quantum information, which is in the matter, which fell into the black hole and formed the black hole, how could that possibly be communicated to the Hawking radiation, which originates in a causally disconnected region from the matter that fell into the black hole, and reach future infinity? Next slide. Okay, so one way to think about this in terms of space-like slices, or for people who work in this field, they're sometimes called nice slices. So those are those kind of curvy blue lines on this Penrose diagram. And you can choose a coordinate system so that each of those space-like slices is a given instant in time. So they, in these, you could choose a set of coordinates where the time coordinate is the same on each of those blue space-like slices that foliate the space. Okay, so all of the events that occur on a given blue space-like slice are simultaneous to each other. And what you can ask is, well, what you can do is look at specific space-like slices which intersect both the interior of the black hole and almost all of the Hawking radiation, which is going to reach future infinity. And because of something called the no cloning theorem, you can argue that the information which exists in the interior of the black hole cannot also exist in the Hawking radiation that's heading to infinity. So this is one particular formulation of the information paradox. I'll focus more on Latour's formulation, which I think is even better than this one, but this is one that I think, roughly speaking, from the 1990s until the early 2000s was the main way that people thought about the information problem. Now, one of the things you can ask is, in quantum mechanics, if I specify the state of my entire system, so here the system is, if you like, the whole universe, if I specify the state of the system on one nice slice, say at early times, I should be able to evolve it using the Schrodinger equation or some unitary operator forward into the future and reach the state which is described as psi f here on the diagram. And because the Schrodinger equation is time reversal invariant, I should be able to take the state psi f and evolve it backwards in time to get back to psi I. The problem, of course, is if I push this nice slice further forward in time, it doesn't cover anymore the stuff that fell into the black hole and eventually hit the singularity. So a nice slice, which is drawn close to future null infinity, that doesn't seem to have enough information that when I time reverse it, it would know all the details of the matter, the matter state that formed the black hole. And in a time reversed description, I should be able to start with the universe at late times, run the Schrodinger equation backwards, and get something which is not actually a black hole, but a white hole, which expels a star. But here you can see that information is lost, and we don't have enough information to actually determine what is expelled from the white hole if I reverse time. So that's another way of describing this information paradox. Okay, next slide. Okay, now one of the weaknesses of all these formulations of the information paradox is that they always assume a fixed classical background geometry. But as I mentioned, when you actually fully quantize gravity, you actually have to think in terms of quantum fluctuations of the graviton itself, or equivalently quantum fluctuations of the geometry. And at that point, the causal structure and the localization of information are much more complicated than so far has been indicated in the analyses. So in fact, what we're going to show now is that the quantum state of the graviton field, which is outside the horizon, actually depends on the internal state of the black hole. So that's a surprising result. That is directly counter to what people say when they draw a Penrose diagram. They say, oh, what is inside the black hole behind the horizon is causally disconnected from everything which is outside the horizon. But on more careful analysis, it turns out this is actually not true. Okay, next slide. Okay, so let me summarize in the next two slides the main result of the first paper. This is the PRL paper. So first of all, you can do the following calculation. You can ask, suppose I have a compact source of energy and momentum. So it's, say, some ball of matter that's in some particular energy eigenstate. And we can ask, what do we know about the asymptotic quantum state of the graviton field of that source? So that's a very well-posed question. I have a source. The source is in a particular state. It's in, say, an energy eigenstate. What can I say about the asymptotic gravitational field of that source? It turns out you can show that, I'll show you on one of the next slides, you can actually write down the state, the coherent state that represents the quantum state of that graviton field. And in fact, that asymptotic state depends explicitly on the energy eigenvalue of the source. And so insofar as there are no accidental energy degeneracies, there's a one-to-one map between graviton states and matter source states. So what that means is that if you take a typical many-body system, those many-body systems, it's kind of a folk theorem in condensed matter physics that there are no accidental energy degeneracies. You only get degeneracies if you have some kind of exact symmetry. So any two very similar states of that matter source will actually have slightly different graviton states when looked at carefully. Furthermore, you can show that if you have a semi-classical matter source, which is itself a superposition of energy eigenstates, that then has to produce a superposition state or an entangled state of the graviton field. Next slide, please. Okay. Furthermore, you can do explicit calculations. So you can do calculations in low energy effective theory of quantum gravity. So taking into account, for example, graviton loops. And you can show that actually there is a long range potential. If you take the simplest possible spherical black hole and you look at the long range potential due to these quantum corrections, you can show that there's actually an r to the -5 term in the potential, where that r is measured in Planck units. And the coefficients of that term actually depend on the internal state of the source. So in the paper, we look at dust balls, which collapse to form black holes. And it turns out the density profile of the dust source affects the coefficient of this r to the -5 term. So that's a very explicit example of how the quantum state of the graviton, because underlying this r to the -5th, the r to the -5th term arises in a quantum effective theory. So it corresponds to a particular quantum state of the graviton field outside the black hole. That quantum state is explicitly dependent on the energy profile or the energy density profile of the dust ball that was used to build the black hole. And so this is a very explicit example of quantum here. Okay, next slide. Okay, so here I mentioned that, so let's go back to this idea of a compact source, which is an energy eigenstate, and its energy eigenvalue is E. What you can show is that the quantum state of the external graviton field corresponding to that source with energy eigenvalue E has the form in equation 1. Now, I've written equation 1 actually in a more familiar form. This is actually the corresponding quantum state for the Coulomb field of a charged object, an object with charge capital Q. And you can see it's built by exponentiating creation operators. Those creation operators are linear combinations of the non-propagating, so the temporal and longitudinal components of the photon field. Exactly how that longitudinal, linear combination arises depends on your choice of gauge. And I use the exponential of that operator and act on the zero charge vacuum to get the Coulomb field that corresponds to an object which has charge Q, capital Q. Now, it turns out in gravity, you just replace this Q with the energy eigenvalue, and you replace the creation operator B dagger for the photon with a creation operator for the longitudinal and temporal component of the graviton. And it turns out this was a known result. This is not actually original to us. This was already known to people. And it arises actually if you try to quantize gravity and you take into account very carefully the Gauss law constraint, you get this coherent state. Okay, next slide. Okay, so as I just mentioned, so both in gauge theory and gravity, the form of that asymptotic state is determined by the Gauss law. It turns out also recently there's been a bunch of work on something called the double copy relationship, which relates tree level graphs in gravity to QED. And you can also derive the same relationship I described in the last slide using this double copy relationship. Okay, next slide. Okay, so now this object I call psi g of E, it means the quantum state of the graviton field. So psi of g means the quantum state of the graviton field. And it's a function of E, where E is the energy eigenvalue of the source. Now, each distinct energy eigenstate of the compact source will then give rise to a slightly different graviton quantum state. And that's explicit in the formula that we showed 2 slides ago, because the E will just appear in the exponent. And if I change E by a very small amount, I get a slightly different superposition when I expand that exponential. I get a slightly different set of coefficients for the B dagger operators operating on the vacuum. Now, a semi-classical matter configuration, like say an asteroid, is not actually an energy eigenstate. Usually we represent it as a superposition of energy eigenstates with support concentrated in some window or some band of energy. So typically we would write it psi equals sum over with some coefficient c sub n of these of energy eigenstates psi sub n. And if I then write down the corresponding quantum state of the gravity field, which corresponds to the semi-classical state of, say, the asteroid, I get a superposition state with the same coefficient c sub n. But now we're describing the actual graviton field, not describing the, say, electrons and protons inside the asteroid. Okay, next slide. Okay, so just to summarize what I've been saying to you, in a way, what I'm saying to you is very familiar, because if you're familiar with effective field theory, you can ask the following question. I have a complicated composite object. Okay, it has a lot of stuff inside it. It's very complicated, but suppose it's a baryon. And so it has maybe 3 valence quarks, and then it has a bunch of glue, and it has fluctuations of quark-antiquark pairs. So it's a very complicated quantum state. But how does a long wavelength photon couple to that object? Well, it couples to the total charge of that composite object. So that's a well-known result in particle physics. But you could ask the same question in general relativity. You could say, suppose, now I'm looking at the figure on the right, suppose you're looking at a long wavelength graviton, but I want to be very careful. I want to ask, how does that graviton couple to a quantum state, the quantum state of perhaps a macroscopic object like a rock or an asteroid? But I want to actually try to be serious about representing the full quantum state of that object. it turns out the results that I've just shown you say that the graviton couples to the energy eigenvalue of that complex object. And to the extent that semi-classical objects that we're familiar with encountering in the real world are actually superpositions of energy eigenstates, then the resulting graviton quantum state will itself be a superposition of specific psi g, those coherent states psi g of E. And that's what's expressed in that formula in the lower right. Okay,
sorry,
next.
Steve, I had a question on this.
Yeah, go ahead.
Yeah, so if I wanted to actually generalize this, shouldn't I be saying something like the graviton should couple to the energy momentum tensor? And is the only reason you're saying energy is because you're not considering, a complicated system that has motion or something like that?
Yes. So in order to get a handle on the physics here, we're taking the simplest possible situation. So we've reduced T mu nu to just the energy of the object. But the more subtle point, which is really what we're trying to get at, and what's really like in these kind of Gedanken, there's more in the paper describing some Gedanken experiments related to this conclusion. The issue is the following. We all know how to do classical gravity. So we know how to couple capital G mu nu to capital T mu nu. But both the quantity on the left and the quantity on the right are classical objects, right? One is a classical gravitational field. The other one is or classical geometry. The one on the right is a classical energy momentum tensor. A related question, which it turns out we had the capability of answering this question all along, which is people didn't think very carefully about it, is let's suppose I'm more serious than that. And I want to say, what is the quantum state of the gravitons that are sourced by the object? So I want to treat the thing on the left, the G mu nu, in a fully quantum mechanical way. So I want to treat it as a psi sub G. And I want to treat the source not as just some classical energy momentum tensor. I want to treat it as a bundle of electrons and protons. What property of that bundle of electrons and protons is actually the main thing that sources the graviton? And in the rest frame of that compact object, turns out it's the energy eigenvalue. So that's the key thing, is the distinction, the move from classical couples to classical to fully quantum mechanical couples to fully quantum mechanical. But notice we can do this in the long wavelength limit. So we don't have to use string theory. We don't have to know what the short distance physics is here. This is just a statement about the long distance quantum mechanics of gravitons. Okay, next slide. Okay, let me just say a few words about this effective field theory calculation that we did. Now, what I have written here is the one loop effective action for quantum gravity. And it's expressed here as a curvature expansion. So what's written here is the first power and second power of the curvature tensor. The coefficients C1, C2, and C3, which are functions of mu, those depend on short distance effects. So as you all know, gravity is not renormalizable, and so there are infinities here. And so C1, C2, and C3 are divergent objects, which you have to know the short distance completion of a theory to actually compute those coefficients. Now, there are non-local terms in this action, which are represented by that box operator sandwiched between the curvature tensor. And those have coefficients alpha, beta, and gamma. But alpha, beta, and gamma are computable directly once you know the particle content of the theory. So they do not depend on the UV completion. So they represent, obviously, since they're non-local, they represent long-distance physics with, say, virtual graviton loops or virtual neutrino loops, whatever it is. And what's interesting is that this effective Lagrangian has been known since the 80s. So it was computed by multiple groups over time, and its properties, the properties of these C's and alpha, beta, gamma were gradually established. But it's only in the last 10 years or so that people figured out how to really use this effective Lagrangian properly, this effective action properly to do effective field theory calculations in low energy gravity. And our calculation is an example of that kind of work. My collaborator, Xavier Calmet at Sussex, his group has been working on effective Lagrangian effective field theory calculations using this action for the last decade or so. Okay, next slide. Okay, so we can do the following. We can take the modified Einstein equations which result from this effective action, and then we can, in perturbation theory, we can compute how the effective action is modified by the extra terms which appear in the effective action, which then modify the Einstein equations. And this is how we find these 1/r to the 5th corrections. And the 1/r to the 5th corrections depend on the internal configuration of the matter which forms the black hole. So the calculation, we did the simplest calculation in the paper. The calculation we did in the paper is for a dust ball, pressureless dust ball, spherically symmetric. But you have a degree of freedom, which is the density profile of the dust inside the dust ball as it collapses to the black hole. And what you find is that the coefficient of the r to the -5th term is itself dependent on integrals over that density profile. So it's an explicit example of how when you treat at least the long wavelength component of gravity quantum mechanically, you find something which is outside the horizon, but which depends explicitly on the details of the object which formed the black hole, and which ends up, all of that stuff, the dust in the dust ball ends up behind the horizon, but nevertheless it leaves a signature which is the coefficient of this r to the -5th term. So it's a very concrete example of how information actually leaks from the black hole interior into the exterior via quantum effects. And so this is an example of quantum hair. Next slide. Okay, so now we're going to shift gears and we're going to use the fact that there is quantum hair. So there is something about the quantum state of the exterior gravitational field, so outside the horizon, which knows about properties, for example, the energy eigenvalue of the matter inside the black hole. And what we're going to try to do is go through the actual evaporation of the black hole, emission by emission of Hawking quanta. And there's nothing really complicated about what I'm about to go through. It's actually basic quantum mechanics. The main challenge is getting the notation, just following the notation, because we have to keep track of all the quantum numbers of the particles and all the things that are happening. And so that's really the only challenging part. There's nothing really conceptually challenging in what I'm about to go through. Okay, so let's assume that the black hole is going to emit exactly n quanta. Now that's an idealization because it could fully evaporate because the energies are not fixed of these quanta that are emitted. It could emit n+1 or n-1, but just to keep the notation simple, let's suppose it evaporates always by just emitting exactly n quanta. And let's define this symbol r1 to be the description. It's a signifier for the first quantum. The r2 is the second Hawking quantum emitted. R3 is the third one, etc. And r(i) stands in for all the quantum numbers of a particular quantum. So delta I is its energy, its momentum is p(i), the spin is s(i), the charge is q(i), etc. But we're just going to use the symbol r(i) for compactness to represent all of those quantum numbers. So the final radiation state will be specified by a list of values for each of the R1 through Rn. Now, we can define an amplitude. So this is a quantum amplitude for the emission of a particular quantum r(i). So that's specifying all the state quantities of that particular Hawking quantum. For a particular set of values for r(i), what is the amplitude for the black hole in energy eigenstate E to emit that particular quantum? So that defines a function, alpha. It's a complex function, alpha of E comma Ri. And you can imagine that alpha depends on E through this external quantum state, psi g of E. Okay? At leading order, in the calculation that Hawking did, he just assumed that he had a fixed semi-classical background. He didn't take into account at all the quantum state of the exterior graviton field, and he gets a certain set of values for these alphas which correspond to thermal emission. But people have known, even since when Hawking wrote his first paper, that there would be corrections to the semi-classical approximation that he originally used. And here we're going to keep track of the full alpha, the full amplitude, alpha of E comma R(i). Okay, next slide. Okay, so let me make some remarks about this function. So in the leading approximation, alpha is just given by the Hawking values. But there are two types of corrections to the Hawking results that have been anticipated for a long time. Some are power law corrections, which depend on the entropy of the black hole to some negative power, and even smaller ones which are exponentially suppressed by the entropy of the black hole. And those would be non-perturbative effects. And So the additional dependence on E and Ri, which is going to appear in our expressions, is something which has been expected by people for a long time. However, they were unsure about how to compute these corrections. And of course, this observation that the quantum state of the external geometry of the black hole depends on the energy eigenstate of the stuff inside, that extra ingredient was missing until now. Okay. So that's what's expressed in item 2 here. The fact that these corrections can depend on the internal state of the whole as a consequence of quantum here. Okay, number 3 is kind of a comment for experts. So even if the corrections to Hawking's results are extremely small, so exponentially small in the entropy of the black hole, it turns out, was shown maybe about 10 years ago, even exponentially small corrections can purify a maximally mixed Hawking state. So the Hawking state, if you write it as a density matrix, looks maximally mixed, but because the dimensionality of the space, which is e to the plus s, because the dimensionality of the space is so large, if you scatter in just the right way very, very small corrections to that density matrix, you can perturb it in such a way that when you take trace of rho squared, you actually get 1. So in fact, you can push what appears to be approximately maximally mixed density matrix into a pure state by making only very, very small, exponentially small perturbations. And that was shown maybe about 10 years ago. And it's important here because even the smallest expected perturbative corrections are capable of unitarizing the evaporation. Okay, next slide. Okay, so let me just track through the evaporation here. So I start with psi I, which is the initial state before any quanta have been emitted. If the black hole's in a semi-classical state, then there's some set of CNs which have their support in some range of energies. And each of those is multiplied by the state, which describes that coherent, effectively that at long distances, it would be that coherent state. Closer to the horizon, we don't have explicit expressions for what it would look like, but it is the exterior state of the black hole as a function of the energy eigenstate En. Okay, so we just have that superposition state. And then we just track through the emission of each of the quanta. So we say, okay, as the first stage, it's going to emit quantum R1. So we sum over all possible states of quantum R1. We weight the outcome by this amplitude alpha, which is a function now of both En and R1. And the resulting state is a quantum state which includes the quantum R1, but now the external graviton quantum state has been modified because it now corresponds to the original states, but corresponding to energies which are shifted down by delta 1. And here I've written the energy and delta specifically, which is the energy of the quantum, but of course all of the other quantum numbers are involved here. So I've just written it as a shorthand, but basically it's a modification of that, the argument of G, which is shifted by all the values, all the quantum numbers that R1 carry. Okay, so we can just continue like this. So let's suppose I want to emit the second quantum. So now I sum over, I was already summing over all of R1. Now I'm going to sum over all possibilities R2. I have now 2 powers, 2 multiplied factors of the amplitude alpha with different arguments. So one argument is for the original state emitting R1, and the next one is for the modified state En minus delta 1 to emit R2. And now the state there includes 2 quanta, R1 and R2, and it describes a external graviton state, which is now shifted both by delta 1 and delta 2. Okay, so you just keep going like this until all n quanta are emitted. Now the final state is just a state of a bunch of Hawking quanta, R1 through Rn. There's no reference to the black hole anymore because the black hole is not there anymore. And there's no reference to the external gravitational field because, roughly speaking, now you're in flat space. Okay, but this final expression is manifestly unitary. So it comes from the time development of the original psi sub I, and it's also manifestly highly entangled. So all sorts of different possibilities exist in this list of R1 through Rn, and they are all superposed with coefficient Cn and also the product of these alphas. Okay, next slide. Okay, so I've just recopied that final radiation state here. As I mentioned, we omit reference to the geometry G now because there's no black hole left. It's just the black hole is completely gone, and you just have a bunch of Hawking quanta that are heading off to future null infinity. And as I mentioned just previously, the final radiation state is a complex superposition. It depends linearly on the initial black hole states. That Cn has just traveled through this entire set of expressions. So it's the same Cn that described the original quantum state of the black hole. And in fact, all the information about the quantum state of the black hole is in these Cns. And you can see that the Cns are also encoded in the radiation state. So there is actually a one-to-one map between final radiation states and initial quantum states of the black hole. Okay, next slide. Okay, now this is the part, everything I did up till now is just notation. It was notation, defining some quantities, and then using those quantities, I could describe the unitary evolution of the black hole. Now, here there's a little bit of a conceptual wrinkle, which sometimes people have trouble with. So, but I'm going to go through it very carefully. So, distinct radiation patterns R1 through Rn correspond to different recoil trajectories of the black hole. So every time the black hole emits a particle, it has to recoil against that particle. And in the process of evaporation, the entire rest mass of the black hole is going to be converted into radiation. So actually the recoils in aggregate are actually non-trivial. And what you can show is that, and this has been known for a long time, for 30, 40 years, is that the uncertainty in the final center of mass coordinate of the black hole, so just as it's about to give off, say, its last quantum, the uncertainty in where it's ended up in this random walk of recoils is actually proportional to the square of the original mass of the black hole in Planck units. So it's much, much larger than the original size of the hole. So you had an original black hole which had a radius of order m, but by the time its random walk through all this entire set of recoil trajectories, the uncertainty in its location is actually of order m squared. So what this means is that if you want to carefully study the quantum mechanics of black hole evaporations, you're not actually talking about a single Penrose diagram. You're talking about many different Penrose diagrams, each of which corresponds to some coarse-grained recoil trajectory of the black hole. And each of those coarse-grained recoil trajectories is associated with some particular subset of the radiation state. So if I tell you exactly the quantum numbers of all the different quanta that are emitted, you can backtrack from that into a particular recoil trajectory of what, by conservation of, say, of momentum, of what the black hole had to do during the what recoil trajectory the black hole had to follow during its evaporation. So there's a one-to-one map between those things. But the thing you can't avoid is that there is a superposition built into this whole, all of these expressions, of macroscopically different quantum states. Okay, let me go to the next slide. Okay, so here are some primitive drawings of this. So on the left, I show a black hole evaporating, and you can see the recoil vector is this blue arrow. And if slightly more momentum ends up going off in the upper right direction, the black hole recoil in the lower left direction. If slightly more energy momentum goes off in quanta going to the upper left, then the black hole will recoil to the lower right. And you can imagine there are different, macroscopically different recoil trajectories that the black hole could follow as it evaporates from some originally huge, astrophysical black hole down to, a Planck mass black hole, which then vanishes. Okay, so because there are distinct coarse-grained radiation densities, so if I coarse-grain over all the quanta that are in the radiation, I just say, well, how much energy momentum is in a particular region of space-time in this particular evaporation pattern versus that evaporation pattern, you can see there are macroscopic differences. That manifests in macroscopically different black hole recoil trajectories. And in fact, it therefore means there are actually distinct space-time geometries, because whenever we make the coordinate transformation to draw that Penrose diagram, we always put the black hole right at the center of the coordinates. So it actually matters whether the black hole is recoiled over to the left or recoiled over to the right in the process of evaporation. You get just different Penrose diagrams. The diagrams themselves look the same, but they're actually representing different space-time geometries. Okay, next slide. Okay, so let me come back to Matour's formulation of the information paradox. And I'll show how these simple unitary expressions that I wrote down actually evade the formulation that Matour gave. Okay, so let me remind you that, again, the Hawking radiation is resulting from quantum fluctuations, so particle-antiparticle fluctuations in the vacuum, which happen just outside the horizon, and one of the pair ends up behind the horizon, falling into the black hole. One of the pair ends up escaping to infinity. But there's no avoiding, because these things are arising from vacuum fluctuations, there's no avoiding the fact that the thing that falls in and the thing that goes to infinity are highly entangled. That these are always highly entangled states that produce the Hawking radiation, and the entanglement is between the thing that escaped to infinity and the thing that fell into the black hole. Okay, so in his notation, B is the thing that can escape to infinity, and E is the thing which falls into the hole. Okay, next slide. Okay, now let's just repeat the argument here so it's very clear. If I have a very big black hole and you're a freely falling observer, so you're falling into this black hole and you've just passed the horizon. As you pass the horizon, you will feel some tidal force, but that tidal force goes to zero the larger the black hole is. Okay, so for a very big semi-classical black hole, there's very little difference between the physics at the horizon and just regular vacuum physics. In fact, for that freely falling observer, there's basically no difference. And so we know everything about the form of these vacuum fluctuations, from which the Hawking radiation originates. Okay, so if there's nothing unusual about physics, no deviation from just standard general relativity and quantum mechanics near the horizon, then we can say everything about the quantum state that produces the Hawking radiation. And it will have the form of this entangled state psi that I've written here. Okay, now at the end of the day, though, the modes that fell into the horizon we lose track of, because they end up hitting the singularity, they disappear from our universe, they're never to be heard from again. If I trace over those modes, those E modes, then I will end up with an entanglement entropy of log 2 in the state. So in other words, if I'm forced to trace over the E modes in this state psi, I get an entanglement entropy of log 2. Okay, next slide. Okay, so what Matour explains is that this just happens again and again and again. So every time I emit a Hawking quanta, I'm starting with a vacuum state. The vacuum state looks just like that entangled state that I've been writing down. I mean, this is schematic. It doesn't look exactly like that. Obviously, it's much more complicated, but it has this form. Okay, it has this essential entangled structure. And because the next quantum that's emitted happens much later, I can write it as a direct product state where, okay, I had a vacuum fluctuation, quantum was emitted, black hole sat there for a long time. Then after a long time, there was another quantum fluctuation where one of the modes happened to fall in. That's the E2, B2 entangled state there. That happens, and it just happens. You just repeat that, and you get this characteristic factorized quantum state describing the evaporation. And of course, this isn't exactly correct. There can be small corrections to this picture, but overall, at leading order, this is actually what the Hawking process looks like. Okay, next slide. Okay, so the B's are the radiation states which make it to infinity. The E's we completely lose track of. If at the end of the day the black hole completely evaporates, I'm left with an entanglement entropy, which is roughly n times, where n is the number of quanta emitted, n times log 2. So I started with a pure state, but I end up with a state with a huge entanglement entropy. So in the language of quantum mechanics, that says a pure state, initially pure state psi, has evolved into a mixed state. Okay, and that obviously violates unitarity, so that's not supposed to happen. And what Matour shows is that you can put all kinds of epsilon corrections. So where if epsilon is some small parameter, you can say, oh, well, actually the entangled state is slightly different from the vacuum state because of the gravitational tidal forces. Or, well, actually there are loops of photons which can affect the evaporation process. There's another epsilon there. So you can, what Matour's theorem shows is that you can modify this result, but as long as the physics corrections to the basic picture are of order epsilon, the final entanglement entropy of the radiation is still proportional to n. It might be n times log 2 minus epsilon, but it still forces you to consider that black holes take a initial pure state and force it to evolve into a mixed state, which is not supposed to happen in quantum mechanics. Okay, so this is, to me, the conceptually clearest formulation of the paradox. And I think most people who work on this problem agree with me. So now let me see how it is that that unitary state, that unitary evolution that I described, actually gets around this mature formulation of the paradox. Okay, next slide. Okay, now again, what he's done here, Matur, is he's analyzed this in a single semi-classical background, right? So when he defines each of these modes, like the B and the E mode, which are fluctuations in the vacuum state, those are defined with respect to a particular vacuum state, which is defined with respect to a particular background geometry, okay? So if you go back to my remark about the recoil trajectory of the black hole and macroscopic superposition states, you can see that two different radiation patterns, B1 through Bn and B1 prime through Bn prime, could be different, not just in a little way, but they could be different in a macroscopic way. And so the formulation in terms of this highly factorized set of entangled states can only be true if I condition on a radiation pattern which does not produce a radically different geometry than the one on which that Matur defines his original E and B modes. Okay, so another way to say that is his formulation of the paradox, although it allows for order epsilon corrections to the process that he describes, it does not consider ever the possibility of entanglement between different background geometries, which we argued earlier because of the recoil analysis actually have to be there. They're actually in this pattern of different possible radiation states. In particular, it's the E modes which are falling in, which are only defined with respect to a particular vacuum state, with respect to a particular geometry. And so you can imagine that there's some other set of things that could have transpired, which are just not described at all in a particular set of mature factorized states. Okay, next slide. Okay, so if I try to map his analysis back to the expressions that I gave earlier, remember, I described the radiation modes as R1 through Rn. Those correspond to his B1 through Bn. I did not explicitly describe the negative energy E modes, which are which fall into the black hole, but instead we tracked the change of the internal state of the black hole. So every time we emitted an R mode, the energy of the internal state went down by delta, and that was then reflected by the exterior metric state, which is G of E minus delta. So the analog of these highly entangled states that Matur writes in his factorized product state are things like what I have at the bottom of this slide. So G of E minus delta comma R, G of E minus delta prime R prime. So those are two different two different Hawking quanta states that could have been emitted. They are correlated to not the E modes, because I don't describe the E modes explicitly, but they're correlated to the external state of the graviton field, which results from the E mode causing the energy eigenvalue of the black hole to decrease by delta. So now if you look, next slide. Yes, so this is just repeating the expressions that I showed earlier, where you just try to keep track of the emission of each of the quanta weighted by these emission amplitudes alpha. And if you look carefully at this expression, now this expression obviously is quite complicated. It's quite a bit more complicated than Matur's because it contains, just because of combinatorics, it contains lots of different possibilities. But if you look inside this, what you'll see is that there are many copies of the Matur factorized state. So if you condition this expression on a particular set of R1 through Rn that describe a particular semi-classical pattern of energy momentum density that then produces a particular semi-classical geometry, then on that semi-classical geometry, you'll see a bunch of entangled Matur states, just like he originally wrote down. But in addition to that, you'll see entanglements between that particular Matur state and some other different Matur states, which are living on a completely different background geometry. So that's the main difference. That's the way that an expression like this actually avoids the earlier formulations of the paradox. It's because this state manifestly doesn't have anything like the factorized form that he assumes, or that results from his analysis of the production of Hawking radiation near the horizon. Okay, next slide. Okay. This is kind of a technical remark, so I apologize if it's not not familiar to most people. So there's a set of results in the geometry of high dimensions, which go under the name concentration of measure. And it turns out when you study quantum states in a high dimensional Hilbert space, these concentration of measure results are highly useful. And there's something called Levyslemma, which describes the degree to which the measure in these high dimensional spaces is concentrated. High dimensional spheres, for example, the measure is concentrated. And so using Levy's lemma, you can prove the following. So if I have a pure state psi in a very large Hilbert space Y, let me now consider a subspace of Y called X, where the dimensionality of X is very small compared to Y. So it's a very small subspace of Y. If I define a density matrix on X, which I get by tracing over the complement of X in Y, then for any pure state, essentially any pure state in the original Hilbert space Y, rho of X will appear maximally mixed. It will appear thermal. It turns out this set of results, which really is a result in pure mathematics about the geometry of spheres, from this you can derive all aspects of quantum statistical mechanics. So that's something that's been realized in the last 10 or 15 years, that basically every result in quantum statistical mechanics can be derived essentially from this concentration of measure property. Now, the way we use it here is that if I consider the full space of radiation amplitudes R1 through Rn, radiation states R1 through Rn, that's a very high dimensional space. It has a dimensionality e to the entropy of the black hole. That's a huge space. But if I force myself to look only at one specific semi-classical geometry that could result, or one specific recoil trajectory of the black hole that could result from the evaporation, I'm forcing myself into a small subspace X. And so even though the full quantum state describing the black hole might evolve in a unitary way, so it's always pure, when I am forced to trace over all of these other geometries that I'm not looking at, I always end up with something which looks approximately thermal. And that's why I get something like the thermal result that Hawking got for his original calculation. Okay, next slide. Okay, so the difference here, the thing that's actually hidden, is the entanglement between different x's and x primes. So the entanglement between different background geometries that correspond to macroscopically different radiation patterns. And if you look carefully at this final state that I wrote down, it exhibits such x prime entanglement. So in other words, if you look at two different patterns of radiation, R and R prime, and choose them so they correspond to macroscopically different patterns of energy and momentum density, you'll see that nevertheless, in this expression, they are entangled with each other. So you cannot factorize them from each other, and you can't write down a factorized expression for the Hawking radiation the way that Latour did. Okay, next slide. Okay, so let me conclude here. So first of all, we've shown that classical no-hair theorems do not extend to the quantum realm. In fact, the quantum situation is exactly the opposite of the classical one. In the classical one, there are a very limited number of properties of the black hole that one could detect from its external hair or its external field. It turns out the quantum situation is exactly the opposite. You can know everything. You can potentially measure all these coefficients C sub n by making sufficiently precise measurements of the asymptotic quantum state of the graviton field. Okay, so that's a very radical shift in our view about where the information is located and how much is recoverable even after matter falls behind a black hole horizon. Now, once we realize that there is quantum hair, and once we realize that the main thing the quantum state of the graviton is coupling to is the energy eigenstate of the compact source, you can then, using simple quantum mechanics, you can actually write down expressions for the full evaporation of the black hole. And you can see that that final expression actually is unitary, and it is able to evade the mature formulation of the paradox because of entanglement between macroscopically different patterns of radiation, or equivalently macroscopic space-time geometries describing the black hole as it evaporates. Okay, let me stop there. I'm happy to take questions.
Okay, thank you, Steve. So my set of hands clapping is a substitute for everyone clapping. So let's see, are there any questions for Steve? I see this from Timothy Raven.
Yeah, I have a question. So the uncertainty in the position of the black hole, your argument is that the uncertainty in the position of the black hole as it evaporates is what's telling you that there necessarily must be different semi-classical backgrounds that you have to incorporate.
Yes.
There's no way to have it evaporate with a single semi-classical background.
Yes. So even if you just take the original Hawking amplitudes alpha. Now, what does that mean? So in the original Hawking approximation, the black hole evaporates essentially like a black body with some temperature.
Right.
And the temperature slowly increases as the black hole gets smaller. But already there, when you have something which is evaporating thermally, it is able to spit the quanta off in all possible different directions. You could have a region which is slightly, has a little more energy going in this direction than this direction. So all of that is actually already present. We know that's present already from the leading order expansion. You can either look at the pattern of radiation that's generated by a thermal body and ask, oh, are there fluctuations in energy momentum density? Yes, there are. Would those not be reflected in differences in the metric? Well, yes, of course they are. And then even more vividly, you can say, well, does the black hole itself actually recoil in some very kind of random walk-like trajectory as it evaporates? Well, yes, that's well known. So there's no avoiding that even in the leading order Hawking approximation, you end up with something that has to look like a superposition of macroscopically different configurations during the evaporation.
Yeah, I guess I would just always assume, at first approximation, oh, the evaporation's isotropic, black hole's not going to move, and I would just forget about the recoil.
Well, the field kind of did.
Yeah.
And it's very easy to fool yourself because you go through all this work into building these beautiful Penrose diagrams, and then you forget each Penrose diagram that you build, it resulted from a very complicated coordinate transformation, which is associated with a particular black hole recoil trajectory.
Right.
So when you show that Penrose diagram that has the black hole fully evaporating, right? So eventually it's gone. Well, that contains that space-time contains the entire recoil trajectory of this black hole as it evaporates. But of course, there are many different ones, and people kind of forgot about that. I think also people are not used to the idea that you could have superpositions of macroscopically different quantum states. However, we now create those in the laboratory. So 35, 40 years ago when Hawking and people were
sure.
That seemed like crazy talk, right? But now we can actually make these things.
Okay, I think Dan has a question as well.
I thought Leonard Susskind solved the problem of the information paradox.
Well, this is an interesting question. So yeah, so great. So I was at the very beginning, I said something about the history of this problem. So I'll say a little bit about it, okay? So Hawking proposed this problem. He writes very strongly in this 1976 paper. He says pure states, black holes cause pure states to evolve into mixed states. This cannot happen. This violates unitarity in quantum mechanics. It violates conservation of momentum, et cetera. It violates time reversal invariance of the Schrodinger equation. So Hawking pointed all this out in 1976. Nobody knew what he was talking about for a long time. And if you read Lenny's book, The Black Hole Wars, it was only in the 80s that Tufte and Susskind, through one-to-one interactions with Hawking, gradually understood what Hawking was talking about. Okay, so it was only very gradually after many interactions that they figured out what was happening. John Preskill at Caltech wrote a very nice and influential overview of this topic, which sort of spread the word that this is a very fundamental problem in physics. Okay, so that only happened by about 1990. When I was in grad school at Berkeley in the 80s, in the late 80s, I read that Hawking 76 paper and did not understand it at all. And I think I asked almost every theorist at Berkeley, what is Hawking talking about? And nobody could explain it to me. Okay, well, this is when I was a graduate. So it took a while for the field to figure out this is a very fundamental problem. Now, in the late 90s, both Tufte and Susskind realized that there is something very special about gravity called holography. And their first papers on this are a little bit unclear exactly what they mean by holography, but roughly speaking, it means that the information that's in the bulk of space-time somehow is also present at the boundary of space-time, and that's what's now known as information holography. And once you convince yourself that's true, you can kind of convince yourself that for sure the information has to get out somehow. It's never really fully confined behind the horizon. The next step in this was something called ADS-CFT duality, where people showed that for very special systems, the evolution of the gravitating theory in the bulk is dual to some gauge theory or conformal field theory, which lives on the boundary. And if the gauge theory evolves unitarily according to quantum mechanics, then the black hole on the inside must do so as well. So there were various arguments that the information problem was somehow solved. Okay, by the time Maldacena wrote his papers, Maldacena and Witten wrote their papers on ADS-CFT, and string theorists started really going crazy about ADS-CFT. At that point in time, everybody believed that the problem would somehow be solved. But the question was always, how does the Hawking radiation know about the internal state of the black hole? What is the actual physical mechanism by which the Hawking radiation is different depending on the different possible internal states of the black hole? And that question was, I would claim, is not answered until you look at these expressions in our paper. So for 10 years after, easily 10 or 20 years after Maldacena wrote his papers on ADS-CFT, if you were to ask Maldacena or Joe Polchinski or Witten, well, how does the information get from behind the horizon into the radiation? They would say, well, we don't know yet. And even just in the last, if you just look at papers on the archive, which were published in the last months, you'll find all kinds of things about non-locality, wormholes transporting the information from behind the horizon into the Hawking radiation. So the actual mechanism of how it works was not understood, even though people strongly suspected that somehow the information does get out.
Okay, thanks.
I see a question from Mahmoud.
Yes. Hi, Steve. Great talk. Awesome work. I'm excited about it, at least. So if I understand it correctly, and this goes back to a paper of yours from about 10 years ago about the momentum states and recoils of the black hole, right? Is there some equivalence in not considering the back reaction, basically, right? So if you were trying to solve this as a quantum field theory in curves in non-stationary spacetime, then you would have some back reaction on the metric, right? And you need to track those states. So my question, of course, is, the context of cosmology is my main interest, but can you see this having implications or some result that you could derive or, say something about, maybe like in de Sitter space, like how does the back reaction, in these entangled patterns, if you can map one-to-one, right, between the B's or the R's and the E's, can you then say something about early times in de Sitter space and the back reactions that might have effects there?
Yeah, first of all, Mahmoud, it's great to see you. I don't think I've seen you since before.
I know, good to see you too, right?
No, it's a great question. So first of all, I always emphasize the recoil of the black hole because that's kind of a known result that everybody agrees on. And it just makes it more vivid that you're superimposing, oh, the black hole did this with the black hole did this. But of course, you could just look at a particular pattern. If I wrote out the pattern of these R1 through Rn's, you would see like, oh, this one has more energy density here, and this one has more energy density here. And so it's just unavoidable. Now, if you, to the extent that your system is described by Schrodinger evolution, you can prove that for almost all initial states, even if the thing is highly localized to begin with, if you follow the Schrodinger evolution of that state, it will eventually include some macroscopic superposition states. Okay, so you can prove this using, there's a 1929 theorem by von Neumann called the quantum ergodic theorem. And you can prove using the quantum ergodic theorem that even highly localized quantum states will eventually evolve into macroscopic superposition states. So if you're doing early universe cosmology, you probably already know this, that when you study the inflaton rolling down, you actually cannot avoid getting macroscopic superposition states of universes with different large-scale structure. Because if the inflaton is fluctuating a little bit, you can have an overdense region here, an underdense region here, but you could always also have an underdense region here and an overdense region here. And if you actually just put it in the Schrodinger equation and crank it forward, you get a superposition of all of these macroscopically different universes, actually. The early people who studied inflation had to all learn about something called decoherence. And they all basically said, well, okay, we're going to end up seeing just one of these macroscopic different possibilities, but they're all there.
Okay, I think Kurtimon is next.
Yeah, hi, Steve. Thanks. It was a very clear talk. I had one question about. Well, first off, you mentioned at some point dual copies, right? And you were also drawing up an analogy between QED and what's going on with the information paradox, right? So at some point, it almost felt like you're referring to the Schwinger mechanism, right? And in QED, and you can do calculations based on that. And as everyone else has pointed out, it seems like people forgot that this object that's causing the electric field, or really the gravitational field, is also a quantum object that you need to consider. So anyway, my question really is something slightly different, which is what is the can you do a similar calculation using the idea of color kinematics duality? And of course, that only applies to flat spacetimes, but would it work as a cross-check? Is this something you've already done? That's maybe my question.
Well, okay, this is maybe not a complete answer to your question, but so first of all, there is a physical analogy that for people who work on this black hole information problem, they always compare it to this other physical system. Like, oh, imagine I just had a lump of coal that I'm burning. Okay, and nobody ever says, hey, a lump of coal burning causes a pure state to evolve into a mixed state, right? People say it about black holes because you have this horizon and the very specific nature of how the Hawking radiation originates outside the horizon. But when you look at it's quite difficult to actually figure out to write down all the expressions for how coal actually evaporates, right? But roughly speaking, you have the same phenomenon for any macroscopic system. So if you have a very big unstable nucleus, or you have burning coal, you have a thing with quantum amplitudes to just spit stuff out over time. And you basically get a similar thing. So you will get, if you really just integrate the Schrodinger equation forward, you will get lots of different potential patterns for the radiation that comes out. And you will see that eventually you get macroscopically different superposition states, which are inside the forward evolved wave function, whether it's a nucleus decaying or it's a lump of coal burning. It's just that normally we think like, okay, because of decoherence, we are only going to measure one of those outcomes. So we just don't care about all the rest of them, but we're going to measure one of them. So I do think that if you took some other theory, like say you had some toy gauge theory with some big unstable objects, and you said, I'm going to have this big unstable object evaporate or decay gradually, and it's going to produce n different things in its decay process over time, you would get a very similar story actually to this.
Yeah, I agree. I'm just trying to. I'm wondering if there's an analogy for this. Like, of course, with the duality, you kind of have to look at scattering of graviton states or scatterings of these non-abelian gauge states. But in this case, how would I even, what would these objects look like, right? Like, what would in a gauge theory, what would this object really look like that is evaporating something?
Yeah. So,
yeah, that's. I'm not expecting an answer. I'm just kind of making a comment.
Well, I will comment that in ADS duality, if you take a small black hole in ADS space and you watch it evaporate, there has to be some dual description in the gauge theory on the boundary. And so that might look like some kind of semi-stable gauge bound state that is just spitting stuff off, because there's no gravity on the boundary, right? It's a pure gauge theory living on the boundary. So there people have tried for a long time now to come up with more, like my old postdoc Nick Evans in Southampton. He's written lots of papers on the of course these are always slightly supersymmetric theories, but like some kind of supersymmetric gauge theory that lives on the boundary. And some hadronic stuff that's happening is dual to something else happening with a black hole in the interior. So I think a lot of people have looked into that, and it's related to my comment that like the evaporation of the burning of coal or the falling apart of a big bound state isn't in a sense that different from what's happening with this black hole. That's kind of the origin of the intuition.
All right, thanks.
Okay, so maybe one last question from Jim. So Jim, did you have your hand up?
Jim, you're mute.
I'm sorry, I muted instead of unmuted myself. Did you have an expression for a different time dependence of the decay?
You
of the
mean
black hole?
you mean does it take a time different from of order m cubed to fully evaporate?
Right, or and in particular the explosion, which I'm interested in because it might manifest as a radiation pattern, temporal radiation pattern in TeV photons because the temperature gets high.
So yeah.
You see anything different?
No, okay. So the standard, so one of the things I probably should have emphasized more in the talk is we're not introducing any new physics. So it's just low energy effective field theory of gravity, but we are trying to treat the graviton in a quantum way. So we care about the quantum state of the graviton, which then can influence the Hawking radiation. These amplitudes alpha to leading order are just the Hawking amplitudes. And so the profile of evaporation of the whole will be exactly what Hawking predicted. So it's the lifetime is of order m cubed. There are small corrections to the semi-classical alphas that Hawking computed. That's been expected for a long time. The argument is that those corrections are enough to unitarize the evaporation. And in particular, you can write down specific expressions which relate the quantum state. The initial quantum state of the black hole is fully specified by these complex numbers C sub n, but those C sub n's appear in the expression for the final radiation state. So that's the argument, is that actually because the quantum state is so complex that's actually being produced in this evaporation, it can actually be a pure state, and it can be a unitary evolution of the original black hole without introducing any new physics. That's the claim. Mm-hmm. So we're not predicting anything different about the sort of macroscopic behavior of a black hole than what, say, Hawking would have predicted.
And if we happen to have be so lucky as have a nearby primordial black hole decay and measure its time spectrum and energy spectrum, you expect the corrections to be relatively small.
Yeah, all the corrections are small. The one thing that's not known is the very final moments of evaporation. Obviously, there's Planck scale physics involved, right. So nobody can compute that. But the early stages, when it say it starts from a gram and goes down to a Planck mass, that's all should be well approximated by the standard results.
Okay, thank you.
Thank you.
I'll let you know if we observe one.
Okay, let me know.
Okay, let's thank Steve again for a very interesting and thought-provoking talk. Again, the video and the slides are going to be on our seminar website.
Thanks, everybody.
Thank you.
Thank you very much.